All right, lesson 1.5, we're talking about rate of change, which is going to be a whole bunch of review for you guys. Squeeze theorem, which theoretically should be review, but again, this is Utah. Some things aren't taught in the core the way they are in other states. So squeeze theorem might be brand new for most of you. And then we'll do a couple limits with some compositions of functions, kind of some cool problems, which we'll expand on a little bit more another day. So first things first, rate of change. Remember, another meaning, a better word for slope is rate of change. And this is something that is going to encompass almost half the year of what we do. We are very interested in the rate of change of a function at specific points. That's half of calculus right there. In this course, there's going to be two different ways, two different situations where you're going to use slopes and rates of change, all right? First one, average rate of change. This is what you've been doing in 9th grade and 10th grade and 11th grade. The average rate of change is the slope between 2 points on a graph. Or the rate of change between 2 points in time. Now, you found this in previous classes using the slope formula. So the average rate of change is the same thing as the slope, which is the same thing as our change in y. How much we change up and down goes on top. How much we change left to right goes on the bottom. The actual formula looks like this: y2 minus y1 over x2 minus x1. That is your average rate of change. That's the slope formula you've been using for years. There's another version of it right here if you were dealing with time, which we're going to do in an example today. Same thing, just on the bottom is values for time instead of values for x. But the graphs look exactly the same. They're just labeled different, right? That's the first situation that you're going to be using this year. The one that we're going to get a lot deeper into as the year goes on is the second situation, the instantaneous rate of change. Now, this is the slope at a single point on a curve. So it's not the slope, the rate of change between 2 points. The instantaneous rate of change wants to know at this exact moment, how much is my rate changing? What's my slope at this exact point in time? And the way that we can do that, I'll show you a couple pictures here, is for now, until we get into chapter 2, you are going to approximate that value, either using the function, the graph, or using the average rate, all right? In chapter 2, we're going to teach you using some calculus techniques how to find that point anywhere on any graph. So here's a couple pictures. So when we're talking about instantaneous rate of change, if you look at this black line up here in the left corner, this line is just going up at an angle. The slope stays the same. The rate of change stays the same. So if I were to say something like, hey, at this point right here, what's the rate of change? Well, it's the same as at this point and at this point and at this point. The rate of change of that line is the same everywhere on the line. The slope is staying the same. Same thing with this red one over on the right. The rate of change right here is the same as right here. In fact, I think it's negative 1/2 is what we're doing. We're going down 1 and over 2-ish, something like that. The rate of change on straight lines is really easy to find even at an instant. On this flat one, the rate of change at every moment, at every point on this line is 0. What gets hard is a curve. The rate of change right here is not the same as the rate of change here, or here, or here, or here, or here. Or in fact, the rate of change right here is not the same as the rate of change right next to that same point. It changes, and that's difficult to do on a curve. Because of that change. So that is it's kind of the core topic of chapter 2 and 3, and probably even a little bit chapter 4. It's one of our main topics. It's one of the main things that we are going to learn about this year in calculus. For now, we are going to approximate that value. You haven't learned the calculus, I'm tongue-tied today. You haven't learned the calculus to actually find it yet. You're going to learn that later. For now, we're going to use the average to kind of approximate what that value will be. All right, so let's do some problems. Example number 1, given f of x equals x cubed minus 2x squared minus 10. Find the average rate of change of f of x between x2 and x3. So if I'm using my slope formula, anytime you are finding average rate of change, anytime you see those words, and you are going to see those words all year long, average rate of change, you're going to use this same formula. So to do this formula, remember I need 2 points. I need a point x1, comma y1, and I need a point x2, comma y2. That just means the x and y values that go together and the x and y value 2 that go together. So it gives me x values. So I already have, I know that my x value for one of my points is 2, and my x value for my other point is 3. Now to find my y value, I have to plug those in. So let's plug x equals 2 in first. So f of 2 is equal to 2 cubed minus 2 times 2 squared minus 10, which is 8, minus 2 squared is 4, minus 2 is also 8. That becomes minus 10. So my value right here is negative 10, my y value. When my x is 3, let's find f of 3. So f of 3 equals 3 cubed minus 2 times 3 squared minus 10. Well, 3 cubed is 27. 3 squared is 9 times 2, that's 18. And then I'm going to minus 10 more. So 27 minus 18 is 9 minus 10. That gives me what? Negative 1. So my y value is negative 1. So now I have my 2 points. I can use my slope formula. I can say, okay, y2 goes first. So negative 1 minus y1, which is a negative 10, over x2 goes first, 3, minus x1, which is 2. So negative 1 minus negative 10, well, that's negative 1 plus 10, so that just becomes 9. 3 minus 2 is 1, so my value here is 9. My average rate of change, my slope, is 9. Okay, let's do another one. This one we're going to do a little, I'm going to just move this out of the, I need more space. I'm going to do this one a little bit different because there's some cool things in calculus, and we'll talk about this a lot in class, but calculus is a little bit different than other classes you've taken. When you've taken other classes, you have had to simplify everything down to as far as you could simplify it. In calculus, there's a lot of situations where you don't. For example, part B, find the average rate of change of f of x between x equals 3 and x equals 4. All it wants, the entire question, only wants the average rate of change. So let's plug these numbers into the formula. I still need an x1 and a y1. And my x1 is 3, and a x2 and y2. My x2 is 4. But instead of plugging in all these numbers, I'm just going to say my y value is f of 3, right? If I plug 3 into the f function, I get my y value. My y value over here is what I get when I plug in 4 to my function. So when I write my equation y2 minus y1, well, y2 is f of 4, y1 is f of 3, and on the bottom, I do 4 minus 3, okay? Now, I know this is a lot different than the last problem. Neither one of these is wrong. They're both correct ways of doing it. I just want to show you something that's a little bit different in calculus with this second one. So f of 4, I have to go a little bit farther. I can't leave it like this because f of 4 means I plug 4 into the f function. So if I do that, if I plug in a 4, I get 4 cubed minus 2 times 4 squared minus 10. That right there is f of 4, okay? See, and I'm going to have to move this already. So let's grab this. I'm going to move it down here. F of 3 comes next. I have to minus f of 3. F of 3 is when I plug 3 in. So 3 cubed minus 2 times 3 squared minus 10. That's on top, f of 3. On the bottom, I still have 4 minus 3. Now, here's what's cool about calculus. I don't have to simplify that. That right there is acceptable as an answer, especially on the free response part of the test. If it asks you to find an average rate of change, you can stop right there. You don't have to simplify. You don't have to multiply everything together. You can leave that as the answer. The problem comes is if you then have to do something with that answer, right? If it says, oh, now use that rate of change to do something else, well, now it's going to get messy and maybe it's easier to simplify. But if you don't have to simplify, don't, because you're going to make a mistake. You might simplify wrong. You might multiply, subtract, forget to carry a negative through that parenthesis. You could make a mistake in the simplification and lose the points for that reason. Anyway, just something cool about calculus that I want you to keep in mind as we do some of these problems. Part C, which of these is likely to be a better estimate of the instantaneous rate at 2.4? So of these two values, one of them we estimated between 2 and 3, and one of them was between 3 and 4. If it wants me to estimate the instantaneous rate at 2.4, it's kind of a no duh that this would be a better estimate, right? The 9 would be the better answer. My answer would be approximately 9 using x equals 2 and x equals 3. Because 2.4 is in between 2 and 3. Why would you use 3 and 4 to estimate 2.4? It might be an estimate, but it's not going to be a very good one. Okay. All right, moving on to number 2. Same idea, but it's presented with a table instead of equations, which is nice because now I don't have to plug numbers in to a big f of x. The data in the table shows the mileage from the start of a 4-hour car trip recorded at 1-hour intervals. Assume the car continued in the same straight line. Okay, so on top I have time in hours, and on the bottom I have miles from start. So this is kind of a distance time problem. And this is one of those where we're using the same formula, but the book gives you this example with time in it. So instead of an X, it's going to be a T. So we might as well, let's follow the book. We'll call this T and this Y. Same thing as calling it X and Y, right? Find the average rate of change of the car for the final 2 hours of the trip. So the final 2 hours of my trip, first of all, that is what? From 2 to 4, that's this time frame right here. So it wants me to find the average rate of speed during that time. So I'm going to use my formula, y2 minus y1 over t2 minus t1. So my values, my t's are on top, my y's are on the bottom. So I'm going to do 250 is my second y value, minus 120 is my first y value, divided by my first t value, or my second t value is 4, minus 2. So I get what, 130 over 2, which is 65. Here's the other cool thing about the AP test. Units don't matter unless it says use appropriate units. If it doesn't tell you to use the units, don't use units. I don't need to put miles per hour, even though that's what this represents. I don't need to put that because it didn't ask me for the appropriate units when it gave me this question. All right. Okay, let's do B. Estimate the instantaneous speed at the 1.5 hour instant. Okay, so if I look at my hours, I've got 0, 1, 2, 3, and 4. I want to estimate 1.5, which is right in between 1 and 2. So let's use those two values right there to estimate my instantaneous speed. This is not an exact answer. This may even be extremely wrong because we can't actually evaluate what, at that point in time, the car could have been stopped for some reason. Maybe a cat ran across the road. We are just estimating with the best information we can use. So my 2 points, I'm going to do, again, y2 minus y1 over t2 minus t1. So I'm going to do 120 minus 55 over 2 minus 1. So 120 minus 55 is what? 65 over 1. Are we getting the same answer? Yeah, we are getting the same answer. Okay. So I'm going to say that because it says estimate the instantaneous speed, my answer is going to say the instantaneous rate of change is approximately 65. And you can say at 1.5 hours if you want. You don't have to. But this right here is the answer I would be looking for. The instantaneous rate of change is approximately 65. Please don't put an equal sign right there. It's not exactly 65 because we don't know that. We're approximating. So be careful with those signs. Part C, during which hour does the data suggest the car reaches the greatest instantaneous speed? This is kind of a cool question because it doesn't really have, I mean, we're using average, but we're trying to figure out in what hour they went the furthest, they went the fastest, which means they also went the furthest, right? If you went faster, you would go farther. So from 0 to 1, they went 55 miles. From 1 to 2, they went, 65 miles. From 2 to 3, they went 60 miles. From 3 to 4, they went 70 miles. So of those two time frames, of those hours, which one did they travel the most distance? And that would be obviously from 3 to 4. So you would say from 3 to 4 hours, they traveled the farthest. Again, that's the best decision we can make based on our information. We have no idea. They could have, in between hour 2 and 3, they could have gone down a great big hill, maxed out their miles per hour and gone 110 for just a couple of seconds. They could have gone really, really fast and then slowed right back down. We have no idea what happened in that time frame. We can only use the table to make our best estimate on what's going on. So, and that's why it says, does the data suggest the car? Those words, we're going to talk a lot about them this year. That's a really big word to use. It doesn't say which hour does the data prove or explain, or it says we're just suggesting that is probably when it went the fastest, right? All right, let's move on. I'm blabbering. Tongue-tied and blabbering. That's a bad combination in the morning. Next topic, squeeze theorem. I love the squeeze theorem. Here is what it looks like. You know what? I'm going to show you what it looks like graphically, and then we'll talk about what it looks like algebraically. So I'm just going to make a coordinate plane really quick, maybe. Ooh, that's so ugly. Sorry, that's going to bother me. Come on, work with me here. It's supposed to there we go. Okay. And then I make it crooked. Of course I do. Anyway, coordinate plane. We're going to pretend like that's a good coordinate straight plane. Let's say I have a curve up here. And let's call this f of x. And let's say that I have a curve below it. Let's say I have a curve right here. And it stays below, maybe right here it touches. Let's call this g of x. Okay, I can say that f of x is always smaller than g of x. Nope, other way around. Bad math. And I'm erasing stuff. Guys, come on. g of x is less than f of x, right? What if I have something in the middle? Let's say I have a function in the middle. In fact, let's just make it a straight line. Let's make this straight line in the middle. And we want it to go, don't snap, please. Nope, I want you right there. Okay. We're going to pretend like that's a good straight line. Let's call this h of x. So h of x is always in between these other two functions. So again, I can say that, let's rewrite this. F of x is always greater than or equal to h of x, which is always greater than or equal to g of x. Okay, that's cool. H is always in the middle. But this gets really interesting when we start talking about limits, because if I look at this point right here, which I didn't draw perfect, but right here, my top function is approaching that point. And let's give this a value, okay? Let's say we're at what? 1, 2, 3, 4, 5.5. So at 5.5, I'm approaching 1, 2, 2. So at 5.5, my f of x is the limit. Maybe we should write this correctly. The limit as x is approaching 5.5 of f of x is equal to 2. The limit as x approaches 5.5 of g of x also is equal to 2. Now here's the cool thing about the squeeze theorem. That means that the limit of h, whoa, bad notation. The limit as x approaches 5.5 of h is also 2. Because the limit of the top function is equal to the limit of the bottom function, the limit in the middle has to also equal that same value because it's always in the middle. And that's the squeeze theorem. And I don't know if I just made that more confusing or less confusing. What it looks like algebraically, okay, what it looks like when you do the algebra, if f of x is less than g of x, which is less than h of x. See, it used different letters already. So f is the bottom function, h is the top function, and g is something in the middle, okay? So here's f, here's g, here's h. If this is true for all x values in some interval, and c is this point right here in the middle, if the limit as x approaches c of f of x equals L, so if the bottom function approaches L and the top function approaches L, then the function in the middle also approaches L. That's all we're saying. If the top function and the bottom function approach the same limit value, the function in the middle doesn't have a choice. It's a no-duh theorem. It has to approach the same value because it's always in between. All right, so examples, and there's only 2 here. We're not going to do this a whole bunch. The graphs of f of x equals x cubed divided by 2x and gx equals negative x cubed over 2x are shown. If you can't tell the difference, the positive, the x cubed is on top, so that's f of x. The negative x cubed is the upside down one, that's g of x. So here's my 2 functions, f and g. Find the limit as x goes to 0 of f and the limit as x goes to 0 of g. So these are nice because they're graphical representations. As I follow f and I get closer and closer to 0, doesn't matter which side I'm coming from, I'm getting closer and closer to 0. So the limit as x approaches 0 of f of x is equal to 0. Now g of x. G of x, if I'm approaching 0 on the bottom, my x 0. If I'm approaching 0, my y value is also approaching 0. So the limit as x approaches 0 of g of x also happens to be 0. Okay, that's all I've asked. Number 4, the graph of a third function k is shown along with the 2 functions from example 3. And then it tells me this. This is the really important information that we need. It tells me that there is no h. It tells me that k is always in between g and f at all points. k is in the middle, and it wants me to find the limit of k as it approaches 0. Well, we already know that the limit of the function on top is 0. The limit of the function on the bottom is also 0. So the limit of the function in the middle has to be 0 by the squeeze theorem. All right? So I can say that because g of x is less than or equal to k of x, less than or equal to f of x, for all real, and that probably isn't even necessary. Because that is true, and the limit as x approaches 0 of f of x equals the limit as x approaches 0 of g of x, which equals 0, by the squeeze theorem, the limit as x approaches k of x is also equal to 0. All right? Because k is in the middle, and because the top and the bottom go to 0, then k has to go to 0 because it's in between those other two functions. This is something you'll use in college if you go further in math. We use this a lot to prove. Sometimes you have a really ugly formula and it's hard to prove things about that formula. So instead, what you'll do is you'll find a formula that's always bigger than it and a different formula that's always smaller than it. And if you can prove things about those two functions, sometimes you can make that proof apply to the function in the middle. It's really pretty cool. We don't use it very much in Calculus AB, but this year, in fact, this is one of the first years that I've ever even mentioned it, because this year on the AP test, there was a question that used the squeeze theorem in it. So I thought we better at least address it a little bit. Okay, last three examples. These are some limits of compositions of functions. So it tells me, and we're going to practice this a lot tomorrow. Well, maybe not tomorrow, next class period. Use the functions graph to find the following limit. So it wants me to take the limit as x goes to 3 of f of x squared divided by g of x plus 1. And then over here on the right, it gives me the function f of x and the function g of x. It gives me a graphical representation of those functions. So it wants me to find the limits as we approach 3. So let's start by things that are on the inside. So f of x. So what's the limit as f of x approaches 3? So here on my graph, as I'm coming up to 3, from here, I hit 2 and I'm down here. And then once I get to 2, I jump up. And as I approach 3, now I'm on this straight line as I go through 3. So that's pretty easy to figure out, that this value right here at 3 is going to be 3. So this piece right here becomes 3 squared, okay? On the bottom, or on the bottom of the function, g of x plus 1. So as g approaches 3, well, as g approaches 3, I'm coming to the right, there's 2, here's 3. From the left, I approach the same point right there, which has a value of 2. So g approaches 2 plus 1, so this becomes 9 over 3, which just becomes 3. So not too bad. Let's look at number 6. The limit as x approaches 2.5 of g of f of x. Okay, so here's where we got to start being careful. We have these composite functions. So the first thing, f is inside. So we've got to see, as I'm approaching 2.5 of f first. So f is this function on the left. 2.5 is right here. And as I approach 2.5, again, I'm on a straight line. So if coming from the left, coming from the right, I'm approaching the same value, and I'm approaching it straight across, and that value is 3. So what I have to do now is, because this approaches 3, I have to rewrite this as, what's the limit as x approaches 3 of g of x? So now I'm not approaching 2.5 anymore. Now I'm approaching 3 on my g function. And we already did that, I think. We did. So as I'm approaching 3 on my g function, I'm approaching this same value of 2. So my answer is going to be 2. That would be my final answer. Now number 7 is the tricky one. And this is the one that if you're going to miss a limit question on the AP test, this is likely to be the one that you miss, because this is an easy one to disregard and to overlook. This time it wants me to take the limit as x approaches 3 of f of g of x. So I'm going to approach 3 of g of x first. All right, so let's go to my g function and approach 3. Now notice, as I'm approaching 3, my x values are, I'm moving to the right, and I'm approaching the number 2 up here, right? My y value is 2. So from the left as I approach 3, I'm approaching 2. From the right as I approach 3, I'm getting up to 2. But here's what I need you to notice. I am coming from below 2. Notice that both sides, I'm approaching 2 from below. I'm not approaching 2 from above, and I'm talking about my y value 2. My function, as I'm going to the middle to 3, my function is going up to 2. So I'm approaching 2 from below 2, from the left of 2. So when I rewrite this one, this is just for me, I'm approaching 2 from below. In the last one, we were approaching 3 straight across, not from above, not from below. We were going straight into 3. This time I'm approaching 2 from below 2. And that means that when I do my next limit, when I take my limit for f of x, I need to approach 2 from below. I can't just take the limit as x approaches 2. I have to approach 2 from below, which is important, because look at my f of x function. If I'm approaching 2 from below, from the left, I'm reaching this point right here, which is 1, right? That has a value of 1. If I'm approaching 2 from the right, then I have a value of 3. The problem is, if I was having to do both of those, this limit would not exist, but I'm not. I'm only approaching from the left. So my answer is negative, and I wrote 1 right there. Come on, man. Negative 1. I think that's a sign that that we need to be done. We're going to practice a lot of those. There's going to be a couple on your homework. I'm looking at it right now. You do have a couple composition functions, and you really got to think through them, but they're good problems. And then there's a lot of review questions on this homework. So homework 1.5, I want you to do all of the problems, but I don't want you to do numbers 22 through 24. So don't do 22, 23, and 24.